Hi everyone, welcome to my channel. In this video, we will see about the ultrasonic welding of tongue and groove concept. Actually, introduction: what is ultrasonic welding? Means ultrasonic welding is a solid state welding technique used mainly for joining thermoplastics. Ultrasonic welding is classified as solid state welding method. It is primarily used to join thermoplastic materials, meaning the materials are joined without melting them entirely, like in traditional fusion welding. It applies a high frequency and low amplitude, which means the process uses high frequency sound waves, typically between 20 to 40 kilohertz. The vibrations have very small movements called low amplitude, ranging from just 1 to 25 microns. These vibrations produce localized heat at the joint interface. As the part vibrate against each other, the energy gets concentrated at the joint area, creating heat exactly where it is needed. The heat causes the thermoplastic material to melt and bond upon cooling. This heat softens the thermoplastic at the joint, and when they cool down, the parts are fused together, forms a strong bond. It is the fastest welding method with typically weld between weld times of zero point 0.1 to 10 seconds. One of the fastest advantages of ultrasonic welding is the speed. Most welds are completely in a fraction of second, making it ideal for high volume production. Let's see some basics of ultrasonic welding, how the schematic diagram will be. Consider this is the upper part of the when you want to join the two plastic parts, consider this is the upper part, and this is the energy director. This is this area, cross area we have shown here is energy director, and this is the lower part, and this is the fixture. This is the fixture. Consider this is the fixture, and this is called horn, and when it get forced to it, and it will vibrate, and it is get heated in this area, and melt and join together. It will complete this complete process will be in a fraction of seconds, like 1 second, all the process will complete. Consider I have two parts here. One is this is the upper part, and this is the lower part. We will see the design guidelines, how much we need to give this tongue and groove. Okay. This is zoomed image of this area. Okay. This is the total thickness, wall thickness. Okay. And a equal to this area, this height, energy director height, and b equal to this energy director base width, which means this width, b equal to this width, and h equal to tongue height. You can say that tongue height, this height, and w equal to tongue width. We can say this width, about this width, and c is the clearance between the upper part and lower part, and g is called groove width. This groove width here it is showing, right? This groove width. Now we will see some design guidelines. D equal to groove depth. This groove depth, if b equal to t by 4, which means this is the main t, and divided by 4, equal to b, this b. Okay. A equal to b into 0.5, which means half of this one, half of this width. And this is for amorphous material, b equal to 0.5, and b equal to 0.86 for semi crystalline materials. H equal to t by 4, w equal to t by 3, h equal to this is equal to t by 3, and width equal to T by 3, this is the same, and C equal to this clearance is 0.05 to 0 0.1 mm. This is the very less clearance. We need to give the clearance. Why? Because if it fuses, means if it melts, this melting temperature melted will go, extra melt will go in this clearance area. G equal to W plus 0.1 to 0.2 mm. G equal to this one, W width plus 0.1 to 0.2 mm. This is the gap, that is the clearance. D equal to H minus 0.13 to 0.25, this one, this height of this one. Okay, and when we consider this part has a thickness of 2.5 mm, then B equal to, I have specified here, B equal to 0.62 mm, and A equal to 0.3, and in the same way for amorphous material 0.3 mm, and for crystalline, semi crystalline material it is 0.5, and H equal to 0.83, and W equal to 0.83, which is the same, and clearance also same. G equal to 1 mm, and D equal to 0.7 mm. This is the basic design guidelines for tongue and groove concept. Okay, now apart from the welding, ultrasonic energy is also used for inserting the metal parts into plastic components. This is used also for inserting the metal parts in plastic components, reinforcing thermoplastics to mechanically fasten dissimilar materials. Okay, widely used in automotive, electrical, medical and packaging industries. See, I have this part, this is the horn, we can call it as horn, and consider this is the metal insert part, this is our plastic part. Okay, if you want to insert it, so it will get vibrated and heated, and the metal part is inserted here. Okay, this is the basic mechanism while using inserting the metal parts. When it comes to advantages of this ultrasonic welding is no fumes or heat generation. Especially in this welding process, there is main advantage is no fumes are not formed, and eliminates need to for complex ventilation. Energy, this process has energy efficient, reduce production costs, quick tooling changes, enabling greater flexibility. If you see any video of ultrasonic welding, it is less than sometimes 1 second is enough for it. Ideal for mechanical design, as it does not introduce contaminants that could affect biochemically. There is no contaminants in it, so that it is very biocompatibility. When it comes to the limitations, current technology limits weldable joints sizes to around 250 to 300 mm. If it is a greater part size is greater than 250 to 300 mm, it is very difficult to weld. Requires special design joint features. That is what the joint features, just we saw that tongue and groove, that to make the stronger groove, special features is needed. Ultrasonic vibrations can damage electrical components. Due to this high frequency, equipment may reduce this cost, reduces damages electrical components, though high frequency equipment may reduce this. Okay, now what he is saying, due to high frequency damage will reduce it. Thank you for watching. Please subscribe to my channel.